Hello everyone, my name is Rohit Ramesh. Thanks for tuning into my talk on functionalization of copper using Thiol multilayers for application in area selective deposition of silicon oxide. This work is in collaboration with EMD Electronics. As you all know, the size of the electronic components and devices have been decreasing over the past few decades and has come down to around 5 nanometers in 2020. In order to manufacture or fabricate such devices, atomic layer deposition process, which deposits monolayers of atoms, is used. Atomic layer deposition process consists of two half cycles, where the first step is the precursor step, followed by the oxidation and co-reactant exposure, which removes the ligands from the surface, depositing the required material. The key challenge with ALD is that it has no control over the lateral arrangement of atoms. In order to find a solution to this, area selective atomic layer deposition process was adopted where there are two surfaces, a non-growth surface and a growth surface. The growth on the non-growth surface is prevented by using inhibitor molecules, which allows selective deposition only on the growth surface. Our work here is based on ASD of silicon oxide on silicon oxide with copper as a non-growth surface. So why is this work unique though? There has been no reports on ASD of silicon oxide on dielectric substrates with metal as a non-growth surface. Also, the reported ASD process use only mild oxidants such as water. The conventional wisdom about silicon oxide ALD is that it requires oxygen radicals for low temperature growth. Also, these strong oxidants can undergo combustion-like reaction with the inhibitors, thus removing them in the process. The inhibitor molecules on copper are usually thiol molecules, where it's a hydrocarbon chain attached to a sulfur head group. Thiols can attach to both copper as well as copper oxide, but in the case of copper oxide, they reduce the oxide to a metallic state and stack as multi-layers. So how do we select the thiol inhibitor on copper for the ASD process of silicon oxide? The first criteria is that the molecule should have a very high vapor pressure for gas-phase functionalization. Hence, molecules with relatively short carbon chains are preferred. Once functionalized on the surface, these thiol molecules should be thermally stable on the surface and must be resistant to atmospheric exposure and strong oxidants. This limits the ALD temperature to less than 150 degrees Celsius. And also, during the ALD process, the thiol molecule should be resistant to oxygen radicals from the oxygen plasma. This can be achieved by minimizing the carbon-hydrogen bonds in the blocking molecules. Fitting all these criteria, and also based on the fact that perfluoroalkyl groups are resistant to combustion, we selected perfluorodecane thiol inhibitor as the passivation layer on copper. The setup for this experiment consists of an ALD reactor with a surface analysis chamber. The in situ setup used here is a reflection absorption infrared spectroscopy. The ALD reactor is also equipped with an inductively coupled plasma source. It is to be noted that RAS is only sensitive to dipoles which are perpendicular to the surface. As in any selective deposition process, we have a non-growth surface, which is a chemically mechanically polished copper, and we create a relevant growth surface by depositing a thin layer of silicon oxide over the CMP copper using plasma-enhanced chemical vapor deposition. We first start with the growth surface studies, where we deposit silicon oxide over PECVD silicon oxide using oxygen plasma-enhanced ALD. The IR spectrum shown here are the half-cycle reactions during the SiO2 ALD process. In the first step, the SiH3 ligand from disecondary butyl aminosilane attaches to the PECVD silicon oxide, as shown by the stretching and the bending vibrations. In the second step, the oxygen plasma removes the silyl radicals and forms silicon oxide on the surface, and also restores the OH groups for the next uh, subsequent ES-batch cycle. The growth per cycle for this process was observed as 1.7 angstroms. Having established the parameters for the growth surface, the next step is to functionalize the non-growth surface using Pfdt and study the effect of oxygen plasma exposure. The spectrum at the bottom is the Pfdt functionalized copper surface, which shows a very high absorbance in the CF2 stretching region. which might indicate a multilayer formation. To investigate this, we studied the surface morphology of the Pfdt functionalized copper using atomic force microscopy. The mound-like features indicated an RMS roughness of about 8 nanometers, which is an order of magnitude more than the bare CMP copper surface. This indicates a multi-layer absorption of thiols on the copper surface, and also correlates well with the previous studies. The Pfdt functionalized copper was then exposed to oxygen plasma, which removed just 15%. It is very interesting to note that the subsequent redox cycle for Pfdt replenished the same 15% that was lost in the oxygen plasma cycle before. This self-limiting trend continued for tens of cycles. Also, this drives home the point that by effectively redosing the inhibitor, the passivation layer on the copper can be maintained throughout the ALD process. Once we have established that PFDT is resistant to oxygen plasma, we developed a three-step ALD process where the first step is the perfluorodiene inhibitor step, followed by the half-cycle reactions of the SiO2 ALD process. The dosing sequence for the ABC type ALD process is as shown here. So what happens after the ABC type ALD process, say for after 35 cycles? The in situ RAS spectra for 35th ABC cycle is as shown here. It is seen that even in the 35th cycle, there is no indication of any absorbance of Silyl radicals in the DS batch step, indicating that there is no silicon oxide accumulation on copper. Now, to further verify this, we did a high resolution XPS spectrum of the Si2P region on copper after 35 ABC cycles. We see that the sample with the inhibitor, there is the intensity of the Si2P peak is almost at the background level, indicating that there is no Si accumulation on copper. And so, answering the next question, does the oxygen plasma oxidize the copper? For the sample with the inhibitor, there were distinct peaks for copper 2p with no signs of oxidation. For the other case, the copper 2p peaks were buried due to the formation of silicon oxide and also due to the partial oxidation by the oxygen plasma. Both these results prove that ABC type ALD process results in no silicon oxide growth on PFDT functionalized copper. So what happens on the growth surface? Does the ABC type ALD process enable selective growth? To verify that, we compared the high resolution XPS spectrum of the Si2P region on copper as well as on silicon oxide, where we see a selective growth of around 6 nanometers for 35 ABC cycles. This indicates the process is selective for more than 5.8 nanometers. The final piece of the puzzle is that can this process be adopted on pattern substrates for real-time industrial applications? To do that, we took a cross-sectional TEM of the pattern sample um, where we analyzed the bare copper silicon oxide pattern. There is a small recess on the silicon oxide region due to the CMP process. Measuring this recess was around 15.8 nanometers before the process. After the 60 ABC type ALD process, the recess went down to 5.5 nanometers, indicating that there is a selective growth of around 10 nanometers. We also did an EDAX mapping of the Si region, where we show that there is no Si accumulation on copper. Also, using tantalum nitride as a reference, we indicate a 10 nanometer growth of silicon oxide on silicon oxide. This indicates that there is no silicon oxide growth on copper. Both these results can be combined to say that selective deposition of silicon oxide was achieved in copper silicon oxide pattern. To conclude, we say that the ABC type ALD process successfully deposited more than 10 nanometers of silicon oxide on silicon oxide, both in blanket as well as pattern samples. We would like to thank EMD Electronics for funding this research project. Thank you.